All right, guys, so today we're going to talk about a little bit of graphing for functions that we've seen before, but we just haven't really graphed very much before. So we're going to do basically what we call reciprocal functions. So it's going to be like a number over a function. We're going to take a look at what those will look like and some interesting methods that we can use to graph it, and also what a linear over linear function looks like, and how we can quickly graph that as well. So we're going to start with number over function. This is like a reciprocal function, so you'll see the function in the denominator and then a number on top, obviously. And then we're going to essentially graph the polynomial in the denominator. You don't necessarily have to put it on the graph, but we need at least a set of points for that polynomial in the denominator. We're going to graph the reciprocal of that set of points. So we're going to reciprocal the y values, keep the x values. And there's a couple things that we will need to kind of understand. So I'm going to just use the first example to kind of explain some of these things to you in bullet point number 2. And if the numerator does not equal 1, we'll have to multiply each y value by the numerator as well. Okay, so let's just take a second and go through some of these steps. So the polynomial in the denominator here is x squared plus 1. So I'm going to start with that function. And normally what you will do is you're going to build a table of values around your x-intercepts. Now, this function is a quadratic that's shifted up 1 unit. So this actually doesn't have any x-intercepts, but I know that this quadratic is going to look something kind of like this, right? So I think I'm going to build it around 0, and then we will get a couple points to the left of 0 and a couple points to the right of 0. So for instance, I think we could get enough information if we did like -2 to +2. Okay, and I'm going to get my y's by just entering each of these x values over here into my equation. And then I'll kind of plot the points. So -2 squared plus 1 is 5. 2 squared plus 1 is also 5. -1 squared plus 1 is 2. Same thing with 1. And 0 squared plus 1 is 1. Okay, so here's our function. Okay, now this is not the graph of f at x. So this is just the graph of the function that's in the denominator of f at x. But I want to just graph this just this time, so at least you guys can kind of see what we're doing when we reciprocal some of these values. Okay, so in order to get the f at x function 1 over x squared plus 1, we're going to keep those x values that we started with. But now what I've done to the function is I have flipped it. So I'm going to take all my y's and I'm going to reciprocal them. So my y's for f at x are going to become 1/5, 1/2, reciprocal of 1 is 1, and then 1/2, 1/5. Okay, there's also something that we need to kind of look at from the original function, the one that we have graphed, and that is that this graph actually goes up toward positive infinity in both directions forever. So if I'm thinking about the really, really high points that I get for this function, when I reciprocal those, what happens when I reciprocal a really large number? What do I get? Pardon? A super, super small number. But can I reciprocal any number and get 0? No. Not really. But as this quadratic here goes higher and higher and higher, the points get higher and higher and higher. And what happens when we reciprocal those is they get tinier and tinier and tinier and closer to the x-axis here. So what ends up happening is that when we have infinite end behavior that goes up forever or down forever toward positive infinity for the y's or negative infinity for the y's, we'll end up with a horizontal asymptote along y equals 0. Because really, really, really large numbers, when I reciprocal them, they become really, really small numbers, but they never hit 0. So that forms this like horizontal asymptote. So in this guy, when I reciprocal this function that has infinite end behavior, we actually get a horizontal asymptote at y equals 0 for the new function. Okay, so I'm going to pencil that in. And then we're going to graph our points here. So I've got -2, 1/5. It's maybe like right here. -1, 1/2. This point stayed the same. 1, 1/2, and 2, 1/5. So we end up with this function that kind of goes like this. Okay, now if we didn't graph anything in between here, we might think that it goes kind of like this in like a V shape, but it actually ends up giving us kind of like a subtle curve toward the top there. So if you're ever not sure, you can always graph a couple extra points in between there. Okay, so that's our function. So this is the function, the red part of this is the function f at x. So we actually don't need this blue graph on here. I just wanted to kind of show you guys that just to illustrate the point of the asymptote and how we get that. Okay, but this is the final function here. Okay, now if I had a number other than 1 up here, I would have also taken these reciprocaled y values and multiplied them by that number. But in this case, it's just 1, so if I multiply them by 1, they're unchanged. All right, let's take a look at another one. Okay, this is number over function, so I'm going to follow the same process that I followed above. We're going to start with x squared minus x minus 2. And what I would like to do is, before we start with this function, I actually want to base my entire table around where the x-intercepts of this function are. So I kind of need to know what the x-intercepts are. So what should we do with this function? We'll factor it. So we're looking for two things that multiply to -2 and add to -1. Jonathan?
1 and -2?
Yeah, 1 and -2. Okay, so our x-intercepts are at -1 and 2. So what I want, in order to get a whole picture of what the graph looks like and what its reciprocal function looks like, I want points on both sides of my x-intercepts and also in between them. So what I'm going to do is I'm going to choose maybe we'll start at -3 so that I have -1 in the middle here, or at least a couple points that are lower than -1. And then once I get to 2 here, maybe I'll go up to 3 and 4, right? So I've kind of based my table of values around where these x-intercepts are, making sure that I have some points below each of them and some points above each of them. Okay, so we're going to take a second and we're going to plug in each of these x values into our function and find the y coordinates. Okay, I'm going to give you guys a couple seconds to do that. We'll pause the video. Okay, what did you guys get as your points here? Someone want to read them off to me? Jeremy, go ahead. What were these two?
I didn't get that.
Okay, what did you get, Jonathan? 10?
Oh, 10? Oh,
Is it 10, 4?
yeah, hold on. So I got, I didn't get 4. I thought I just didn't get 3.
Okay, what are the points, guys?
Aaron, go.
Go, Aaron.
I got 10, 4, 0, -2, -2, 0, 4, 10.
Okay, that makes sense. Okay, so
-3, 10, then 4 is 10.
what?
Oh, wait, yeah, you're right.
Okay, so if we kind of graph this here, well, we don't necessarily even really need to graph it, but the important idea here is that I have basically, we can't really fit -3 and 4 on there, but we're still going to use those points. But I just want to show you guys what we kind of have. Yes. So we have a vertex somewhere in between here. So it might be helpful for us to also find the point where x is equal to 0.5. Can we plug that into our calculators for this function quickly here, just so that we know where the vertex is? Because that's kind of an important point of a quadratic. -9/4.
That would be just over 2.
So yeah, that's 9/4, yeah. So -2.25, so it's like right here-ish, right? Maybe like closer up. Something like that. Okay, so here's our function. This is not the reciprocal function. This is the original function that's in the denominator of this. So what we need to do in order to get our reciprocal function is we need to first reciprocal the y values.
Except then we have to multiply -2.
Yes, that's what we're going to do after. You could do that all in one step, but I just want to show it for this one. Okay, so you've got 1/10, 1/4. What's the reciprocal of 0?
Undefined.
It's undefined. What happened when we reciprocaled zeros when we were graphing the secondary trig functions? Liam? Vertical asymptote. So I have a vertical asymptote at -1. And also at 2. So do you guys remember from our reciprocal functions, we said zeros become vertical asymptotes when we reciprocal them? So I now have 2 vertical asymptotes at those zeros. Also, what do we know about when we reciprocal infinite n behavior? What did we talk about in the first example? What else do I also have now? Say it louder. We have a horizontal asymptote at y equals 0. This is because we got reciprocal of infinite n behavior. Okay, which essentially just means if I get really, really big values and I reciprocal them, then I get really, really small values. So they're approaching 0. So I also have a horizontal asymptote along the x-axis here. Okay, and the last thing that we need to do before we actually start graphing these is I need to take my y's and multiply them by the value in the numerator. So we're going to multiply them by -2. X's stay the same this entire time if you've kind of noted that. That's good. So I've got -1/5 for these, -1/2. This is still a vertical asymptote for -1 and 2. And then we get 1 and 1 and 8/9. Okay, so let's graph these points. So at -3, I've got like -1/5. That's going to be a pretty tight in there. And same thing at 4, we've got -1/5. And then -2 is -1/2. Same thing with 3. And then we have 0, 1, 0.5, 8/9. So that's kind of like pretty close to 1. And, oh no, sorry, I graphed that in the wrong spot. Here, and 1, 1. Okay, so here's kind of what's happening. Remember, your graph needs to kind of curve around the asymptotes. It doesn't touch them. So the middle part here is kind of like a little parabola almost. And then the sides will curve around the asymptotes here. So we've got points that are kind of doing this. Oops, sorry. So that is our function. And we should probably label these as well. X equals -1 and x equals 2. All right, so the green parts are our function and the blue parts are the asymptotes to that function. You don't necessarily need to graph the red graph, but you will need to create a table of values and you'll need to identify where those x-intercepts are so that you can kind of build around the x-intercepts. If I didn't have the points on these sides of the x-intercepts, I would be missing part of my reciprocal graph. So I always want to make sure that I'm kind of putting my x-intercepts in the center of my table of values and then I have points on either side of those x-intercepts. Right? So I'm making sure that I have points that are lower than 2 and bigger than 2, and same thing with -1. They're bigger than and smaller than on both sides. Okay. Next type of function is our linear over linear function. And the way that you're going to be able to identify these is you have a degree 1 polynomial over another degree 1 polynomial. So these guys that we just looked at, they're number over function. They won't have any x's in the numerator if you're going to graph using this method. These ones that we're looking at, they're linear over linear. And there's some quick little pieces of information that we can get from our functions. The vertical asymptote of the function comes from the 0 of the denominator. The horizontal asymptote is the ratio of the coefficients of the x's. This is where we're going to get our vertical asymptote from. And once we have that, we actually have a point over which these are kind of like reflected over where the asymptotes cross. So I'm going to show you what I mean when we do an actual example here. But they kind of have this like diagonal symmetry across that point over which the asymptotes cross. And then I usually use the x-intercept and one other point. It can be any point on the function. Usually I'll use the y-intercept if it's not at on an asymptote. Okay, so let's use this function as an example. The vertical asymptote. Okay, this is no different than how we find restrictions normally for any rational expression. So what can x not equal? What's the vertical asymptote? Jonathan? -2. It comes from the denominator, right? So x equals -2 is the equation of the asymptote, but we know this is a restriction of the function. So that's where that comes from. We're going to pencil that in. Okay, there's also a horizontal asymptote for these functions, and it comes from the ratio of the x coefficients. So what are the x coefficients here? Liam? They're 1 and 1. So the horizontal asymptote will be 1 over 1, which gives us 1. So we're going to pencil that in as well. Okay, so this point right here is not a point on the function, but the point where the two asymptotes cross is actually the point of symmetry over which we can count to the opposite side of the asymptotes and actually reflect points to the diagonal side. So I'll show you what I mean once we actually have some points that we can work with. X-intercept. X-intercept comes from the numerator. What's the 0 of the numerator? Yeah, so it's 3, 0. So we have a point at 3, 0. And the y-intercept is actually the ratio of the constants. So that will be the y-intercept there. So what is our y-intercept? -3 over 2, yes. So -1.5. Oh, sorry, that's on the y-axis. Okay, so that gives us 1/2 of our function here. So my graph kind of does this. And what we need to know about linear over linear functions is that they always have a symmetrical piece which is reflected diagonally across on the other side of where the asymptotes are. And I can actually count to this point of symmetry here, this little symmetrical piece right here where the asymptotes cross, and then reflect my point to the other side. So everybody, I just want you to watch up at the front for right now, and then I'll give you guys a second to copy it on your own. But I'm gonna look at this point to start. And what I'm gonna do is I'm just gonna count the number of units until I get to this cross section of the asymptotes. So it's gonna be 1, 2, 3, 4, 5 units to the left and 1 unit up. Okay, so then I'm gonna do the same thing once I hit this point. I'm gonna go 5 units to the left, 1, 2, 3, 4, 5, and 1 unit up, and that's the reflected point. Okay, we'll do it one more time with the y-intercept. So the y-intercept, I'm going to count to this cross section here. So it's going to be half, 1, 2.5, up, 1, 2, left. So we're going to go 1, 2.5, and then 2 units left, 1, 2. And there's my reflected point right there. Okay, so I'll give you guys a second. You can plot those points. Okay, and the function should look like it's symmetrical, should look like there's some form of balance happening here where this piece kind of looks like it's been like flipped over and kind of reflected over onto that side. Okay, any questions about that? So we're just counting the number of units over and up or over and down to that cross section of the asymptotes and then counting that same number to get the reflected point. Okay? All right, do you guys want to try one?
Yeah.
Okay, you guys try the next one. I'll give you guys a couple seconds. All right, can somebody tell me what the vertical asymptote is? Alexandra, what'd you get? X equals 1, that comes from the denominator. So we're gonna pencil that in here. Label it. Horizontal asymptote, what'd you guys get? 2. So that came from the coefficient of the x's here. So that's y equals, technically it's like 2 over 1. We get 2. So that's here. X-intercept.
I got 3 over 2.
Okay, that comes from the numerator. So that'll be 3 over 2, 0. So that's 1.5. So right here. Okay, and y-intercept. 0 and 3, yes. -3 over -1. So that is here. So we have kind of like 2 on opposite sides. So can I reflect 1 onto the upper side and then the other one onto the lower side? We'll just count both ways. Okay. So what? Yeah, we can. Of course we can. So for this point, this purple point, I'm going to start with this. We'll go up 1, 2, and left half. So we're going to go left half and up 1, 2. And we get a point reflected here. So that's the reflection of the purple point. Left 1/2, yeah. Or, yeah, just a half, yeah. Okay, and then for the green point, let's count. We're going to go down 1 and right 1. So for this one, we'll go right 1 and down 1. And now we have a new point at 2, 1. Okay, so now we have 2 points on either side. We can make our curve. So we're always counting the distance to this cross section between the asymptotes and then just counting that same distance on the opposite side. Does anyone need to see that again, or are we okay? See it again? Okay. So I'm going to count the distance. So I had this point and I had this point to start. So I'm going to count the distance from this point to this cross section of the asymptotes here. So it's going to be 1 unit, 2 units. I guess you can't see that super well. It's going to be 1 unit up, and then another 1 unit up to get to the asymptote, and then half a unit over to get to this cross-section point. And then I'm going to do the same thing. So I'm going to go over a half, and then up 2 units, and that's how we get this point right here. So I'm just counting how long it takes me to get to this orange cross-section, the cross-section between the asymptotes, and then counting the same number of units and reflecting it diagonally on the other side. Okay? Is that good, Fayak?
Yeah.
Okay. Any questions? Okay, so you're going to look out for 2 things. These are 2 kind of different graphing processes, right? We're going to look out for number over function. That's the reciprocal. That's where we graph the function in the denominator and do the reciprocals of the y's. And we're going to look out for linear over linear. Because for that one, I think this process is pretty quick to graph it. You can find the asymptotes pretty quickly and then find a couple points and just reflect them on the other side. So look out for those 2 different ones because we're going to use the 2 different processes depending on which type of function we have. Okay?